In this section, we're going to be talking about how to get the basic look of a graph. Not all of the details, but just a general idea based on just a few pieces of critical information. So the first thing we say is that given a polynomial with lead term kx to the p power, then the degree of the polynomial is p and the leading coefficient is k. So this is just a recall, just something that hopefully you've seen before, and maybe we've even covered this in past videos. But we're just going to go ahead and do a quick practice with it, as this lead term concept and degree and leading coefficient are going to be critical for this section. So for this example, we are going to find the leading term, the leading coefficient, and the degree of f of x equals negative 3x to the 4th power plus 2x to the 6th power plus x to the 8th power minus 2x to the 5th power. Okay, so it's important to remember that the degree of a polynomial is the largest exponent. And that term, the term that contains that degree, is the lead term. So starting off, what is the lead term? Well, it's the one with the largest exponent, which ends up being this x to the 8th power. It's just plus x to the 8th power, so there's nothing in front of it, no constant that we need to worry about, which means the lead coefficient is just going to be 1. If there's nothing showing in front of it, then that means it's technically times 1, so the lead coefficient is 1. And finally, from there, the degree is that exponent, the largest exponent, which is 8. So we have our lead term, lead coefficient, and degree. Okay, so with that, we now have some cases given the lead term kx to the p power. The first case is if k is positive and p is even. So you have an even exponent and a positive leading coefficient, then both ends of the graph will go up. Meaning, just a quick example, your graph would look something like this. We have no idea what's going to be in between these yet, but we do know that the graph will start going up and to the left and will finish going up and to the right. From there, we say that if k is less than 0 or k is negative and p is even, then both ends go downward. And in this case, the graph might look something like this. Again, though, we do not know what's in between. We just know that both ends will point down. So it's important to note here, whenever you're dealing with p, the degree, being even, both ends will go together. They'll either both go up or they'll both go down. And they'll both go up if you're dealing with a positive leading coefficient, and they'll both go down if you're dealing with a negative leading coefficient. When p is odd, however, the ends go in opposite directions. So if p is odd and the leading coefficient is positive, then it will start in the bottom left and it will work to the top right. A way to memorize this is think about the graph of x cubed. X cubed has a positive leading coefficient and an odd exponent. What does that graph look like? Well, it looks something like this. Again, we don't care about what's in the middle, we just care that it starts in the bottom left and it ends on the top right. The same thing is true back here for when p is even. An easy example of that would be x squared, where we have a parabola. It starts in the top left and ends in the top right. So always use these basic examples as references to memorize the entire process. So k being less than 0 in our fourth case and p being odd means a vertical reflection. We're going to take this graph and flip it over the x-axis. It's going to start in the top left and work to the bottom right. So it will always start in the top left and end in the bottom right when p is odd and k is negative. And again, these are just basic reference examples. We have no idea how many hills or valleys or where they are in this problem. Okay, so with that, we're going to decide whether the degree is even or odd, and if the leading coefficient is positive or negative. So starting with the degree, is the degree even or odd? Well, it starts in the bottom left and it ends in the top right. If the ends of the graph go in opposite directions, that means it is automatically an odd degree. If they went in the same direction, both up or both down, it is an even degree. And now from here, is the leading coefficient positive or negative? Well, it starts in the bottom left, it ends in the top right. Remember, that's just like our graph of x cubed, starting in the bottom left, ending in the top right. So in this case, what does that tell us? Well, it tells us we must be dealing with a positive leading coefficient because it has the same starting and ending arrows as the graph of a positive leading coefficient with x cubed. So our degree must be odd and the leading coefficient must be positive. Working with the terminology we were using in the previous cases, this would be the same thing as saying k is greater than 0 and p is in the odd numbers. Always remember this curved looking E means in or within. Alright, so from here we introduce another definition. We'll say that a turning point or local extremum, this is also called an extrema if there are more than one of them, is the point where the slope changes from positive to negative or from negative to positive. So if you think about what that looks like, if your slope is positive and then suddenly changes to negative, what do you have? A hill. This point is the local extremum or turning point. And if your slope is negative and then suddenly changes to positive, so it's going down and then suddenly goes up, then you have a valley, which means this point at the bottom of the valley is the local extremum or turning point. So we say that a polynomial of degree n, so if the degree is equal to n, it will have at most n x-intercepts and n minus 1 turning points. So for example, if we talked about that problem that we had at the beginning of this video where the lead term was x to the 8th power, that means the degree is 8. So the polynomial has a degree of 8, which means that it has at most 8 x-intercepts and 7 turning points. You take your degree to find the number of possible x-intercepts. It's not saying exactly, it's just saying at most there will be 8. There could be 6 or 4 and so on, and we'll talk about that in a later section. And the number of turning points will always be at most 1 less than the degree, so 7 in this case. So let's go ahead and try an example. We want to find the maximum number of x-intercepts and turning points of f of x equals 3x to the 5th plus 7x squared minus 0.5x to the 7th. take a moment, pause the video, see if you can't decide. Okay, so trying this together, the number of exponents, the number of x-intercepts, there are at most 7 x-intercepts, and we know that it's at most 7 x-intercepts because the degree is 7. That's the largest exponent we're dealing with. And then from there, we have at most 7 minus 1 or 6 turning points because we are to subtract 1 from the degree. And I'm just going to go ahead and circle this with both of these. This is terrible circling, but it's important to note that the at most goes with both of these. At most 7 x-intercepts and at most 6 turning points. Again, I apologize for the circling here. I just ran out of room. Okay, so from here, our next example, we're going to determine the minimum degree of the previous graph. So looking at this graph here, what is the smallest degree possible? So let's take a moment to look this through. First of all, we know the degree has to be odd. Now from here, look at the turning points. We have 1, 2, 3, 4 turning points. And remember, this fact says you will have at most n minus 1 turning points. So if the graph has 4 turning points, then that means the degree had to be at least 1 more than the number of turning points. Whenever you're working backwards, instead of subtracting 1, you're going to add 1. So because there are 4 turning points, that means the degree has to be at least 5. That doesn't mean it is 5. It could be more than 5. But it has to be a minimum of 5 in order to have 4 turning points. If we said the degree could be 3, then if you subtract 1 from 3, you'd get 2, which means there would be at most 2 turning points. But we already saw there are 4, so that's impossible. There has to be at least 5 for the degree so far. Now we also have to check the x-intercepts because the degree is based off of those as well. There are 1, 2, 3, 4, 5 x-intercepts. So because there are 5 x-intercepts, then that means the degree has to be at least 5 again. So the degree has to be at least 5 from the turning points, it has to be at least 5 from the x-intercepts, and it has to be odd. So what can we say? We can say the degree is at least 5 and odd. Because again, from what we did earlier with that graph, we knew that the degree had to be odd since the end points, the arrows, went in opposite directions. So the degree has to be 5 or 7 or 9 or 11 and so on. Any of those graphs, any of those degrees that is, will satisfy this graph having 4 turning points and 5 x-intercepts. Okay, so from there, we want to find the maximum number of x-intercepts and turning points, then find the x-intercepts given f of x equals 2x to the third plus 3x squared plus x. Alright, so to start off with, we need our degree. The degree in this case is the largest exponent, which is just this 3. So that means in terms of x-intercepts, there are at most 3 x-intercepts. It's always equal to the degree, at most equal to the degree, I should say. And then from there, the turning points, we take our degree and we subtract 1, which tells us that there are at most 2 turning points. So again, we're going to put an at most here, because again, there is no guarantee that there are exactly this many, but this is the first part of the problem. There are at most 3 x-intercepts and at most 2 turning points. And now we actually want to find the x-intercepts. And we can do this fairly quickly by just remembering that you always set the equation equal to 0 to find your x-intercepts. So 2x to the third plus 3x squared plus x equals 0. If we factor this, we can factor out a common x, which gives us 2x squared plus 3x plus 1 equals 0. And now we can factor this as well. We need to factor 2x squared plus 3x plus 1. We need 2 numbers that multiply to give us 2x squared, so we'll try 2x and x. We need 2 numbers that multiply to give us 1, that's 1 and 1. And we need the numbers to multiply to be positive and to add up to be positive, so they both have to be positive. Let's check if this worked out. 2x times x is 2x squared. 2x times 1 is plus 2x. 1 times x is plus x. And 1 times 1 is plus 1. Adding these two like terms together, we get 3x. So it did work out. We factored this properly, which means we can now set each factor equal to 0 to find our x-intercepts. So we get x equals 0, 2x plus 1 equals 0, and x plus 1 equals 0. The first one's already done for us, just x equals 0. The second one, we're going to subtract 1 from each side to get 2x equals negative 1, and then divide each side by 2 to get x equals negative 1/2. And over here, we're going to subtract 1 from each side to just get x equals negative 1. So what are our x-intercepts? The x-intercepts are the points 0, 0, negative 1/2, comma 0, and negative 1, comma 0. If you're wondering where all these y values of 0 came from, that's because we set the equation equal to 0. We set f of x equal to 0. That represents the y value. Alright, and now finally, for our last problem, we want to determine the degree and whether the leading coefficient is positive or negative. So this is very much like our previous examples, just combined into one. I want you to take a moment, pause the video, see if you can't go through this problem. Get as far as you can through it. Okay, so trying this together. The first thing that we should note about this is that it has 1, 2, 3, 4, 5, 6, 7 turning points. So the number of turning points is 7. And remember the degree, if you take your degree and subtract 1 from it, that gives you the maximum number of turning points. So working backwards from turning points to degree, we have to add 1 to the number of turning points to find the minimum degree. Which means because the number of turning points is 7, then the degree is at minimum 8. If you just check that really quick, if you take a degree of 8 and subtract 1 from it, it would give you that 7 turning points. But if you took a degree of 6 and subtracted 1 from it, it would give you a maximum of 5 turning points. We already have 7, so we know the degree has to be a minimum of at least 8. From here, we look at the x-intercepts. We have 1, 2 x-intercepts, which means the degree has to be at least 2. That doesn't help us very much because we already know the degree has to be at least 8, so we can just ignore that for now. We just need to use this 8. The minimum degree is 8 so far. And now finally from here, both of the arrows go upward. That means the degree has to be even because they are both going in the same direction. The degree has to be even. So what does that tell us about the degree? It is a minimum of 8 and it is even. Alright, from there we finally check the leading coefficient. This comes from the fact that both arrows are pointing up. Remember, if they're both going upward, then the leading coefficient has to be positive. If they were both going downward, it would be negative. And that solves the problem. The degree is a minimum of 8 and even, and the leading coefficient is positive.